All right, now we've been writing some code, right, for our process control block.
Oh yeah.
Switch.
We tried to break.
Oh yeah, we tried to break Java.
Yeah.
That's right.
That didn't work well.
Why is oh. Okay, Eclipse is dying. Let's put it out of its misery. Safari web content. What happened? Are you talking about me, Abe?
No, my Eclipse is working and his is about to open twice before mine thinks it's about opening.
Maybe he's got a better computer.
He does have a better computer.
Well, that's what you get for buying a Mac.
I didn't buy it.
Oh. Was it like an old Core 2 Duo or something?
It's a early 2011 model.
So what's the processor in it?
I think that, yeah.
You don't even know. Click on the Apple.
I was just saying.
Click on About This Mac.
Like I said, things are still loading, so it doesn't really work.
Are you running Yosemite?
Not yet. Not yet. That's his problem.
Cannot find SDK folder. Okay. All right. Is this us? Oh, this is us breaking it, right? All right. We'll just assume that was a complete success. Well, we all believe it is breakable, right? You eventually do run out of memory on your computer, or memory that Java grabs. All right, so far in our process control block, we have our program counter and our process state. Program counter keeps track of where we are in a program. Process state keeps track of the current state of the process. Now, are all processes, do all processes have the same number of lines of code? No, of course not, right? So what we want to do is when we create a PCB for our little simulation, we want to create a range of lines of code, okay? And we're going to make this fairly, well, let me think about, we want it to be a somewhat realistic simulation. So what we're going to do here is we're going to have an array, which probably wouldn't be how it's originally implemented, but we're going to implement it that way. Your beeper? Do you really have a beeper, a pager? Oh. Does anybody in here have a pager? IT guys. All right, so we're going to go ahead. We're going to create an array, and we'll make this an array of strings just for the sake of nothing. We'll just call this the code. And we're going to go ahead and inside our constructor for PCB, we're going to randomly generate how many lines of code. Then we'll fill up our array with those lines of code. We're just going to call it line 0, line 1, line 2, line 3, something like that. So somewhat of a waste of time, but we want to give our CPU that we're going to be writing sometime soon something to eat. Okay, so this is kind of doing it for simulation's sake. All right, so we're going to use our random class, which we'll need to import java.util for. And we're going to say that most programs are going to have between, well, most programs for our simulation are going to have between, how many lines of code? 500 and 5,000? Reasonable range. All right, so we're going to say int num, actually we don't even need to say int num lines. we can say the code is equal to a new string array of size r dot next int ooh, we don't have one that gives us a, this will work. R dot next int, we said 5,000, right? So we're going to say 4,901, and then we'll add 100 to that. So this will generate us a number between 0 and 4,900. Plus 100 will give us a number between 100 and 5,000. All right. So this is just the number of lines of code that's going to be in this this program, and then we'll put a little comment: fake loading code from memory. Keeping in mind, when we get farther into memory management, we're going to talk about how virtual memory works. So realistically, you wouldn't load every line of code into the array right off the bat. You'd load a subset of them. But we're going to load all of them just for our example here. So we'll say for int I is equal to 0. I is less than the code dot length I plus plus. And we'll say the code at bucket I is equal to assembly code concatenated with I. So we'll have assembly code 0, assembly code 1, assembly code 2, blah, blah, blah. That's our program. All right, because we are not going to write a assembler for interpreting those lines of code. We're going to fake it. Okay, so now process control block has a state, which starts off as a new state. We then fill it up with our code. Then we set the program counter to 0, beginning of the code. Now, once it's loaded into memory, that's what we just did. We've loaded it. Let's just say that this is loading it into memory for our example. Okay? Once it's loaded into memory, at that point in time, actually this is into memory. At that point in time, we can change this dot process state is equal to process state dot ready state. Okay? Keeping in mind that in our example here, this is going to run through pretty quick. But in a real operating system, the act of taking something from hard drive, loading it into RAM, making it available to the PCB may take some time relative to how fast the CPU is. It's going to happen pretty quick. When you double click on Microsoft Word, it launches pretty quickly-ish. But, you know, in reality, this could take more time than it's going to seem like it takes for us. So from our perspective, it's going to start off as a new state and almost immediately turn into a ready state. Okay. I guess that's with the recursive forking. Makes sense. Ah, yes. Ah, yes. Oh, I saw a news article this morning that apparently Wisconsin bars gave out a record number of touchdown shots yesterday. Man, that game could have been so much worse if Rodgers would have played in the second half. For those of you who didn't watch, the Bears lost.
Bad.
Was it 48 to nothing at halftime? I think they went over 50 in the second half. Yeah, it was bad. When you're down by 50 points at halftime.
There's no mercy.
Yeah, now let's get some of those second strings in there and let's practice. Even the Bears played along. All right. we now have to have our CPU registers. And for our little fake CPU, we're going to pretend like there's 4 registers. Okay? And these CPU registers, they're going to hold, go ahead. You think? Haha. All right, so we're going to have 4 registers. Now, for our argument, we're going to have each register is going to hold an int. Called the registers. We'll say this dot the registers is equal to a new integer array 4, capable of holding 4 pieces of information. Now, as we're thinking through this, if you're the operating system writer and you are creating a PCB for a specific operating system that runs on a specific architecture CPU, the number of registers is going to be related to the architecture of that CPU. Does that make sense? So often, what we would have is we might have an object called architecture. And that architecture would tell us the number of registers, the number of these different things. Okay, we're not going to get that deep in our example, so we're just going to assume 4. All right. Now, really what we should do is we should probably have our lines of code work with those registers in a simplified case. We're going to go ahead and initialize all the registers to 0. In fact, actually, let's just do this. The registers is equal to I have to do it up here. So our registers has 4 things in it, initialized to 0 for all of them, which seems to be in line with what Java does for buckets of an array or variables. Seems to make them 0. Not a big deal for us. Now, when we're going through and we're creating our lines of code, we want to create these lines of code in terms of our registers. Okay, we're just going to assume every line of code has something to do with a register or its I/O. That makes sense? So, when we're setting up these lines of code, rather than say assembly code 0, assembly code 1, assembly code 2, we're going to have 2 different instructions. We're going to have a move instruction, which moves a value into a register, and that value can either be a literal or it can be the value of another register. And then we're going to have an I/O instruction, which will cause the CPU to get interrupted. Make sense? In our simplified CPU. We're moving numbers around or we're interrupting the CPU. So we'll use our R here. So we'll generate a Boolean. So this first one says, should we do I/O? So we're going to roll the dice, and if we get a true out of that, we're going to generate a Boolean. If we get a true out of that, then we're going to say the code at bucket I is equal to I/O, which should flag an interrupt as we move further down the line here. Okay? Else, we're moving a value. All right, so we want to either move a literal into a register or we want to move the contents of another register into a register. All right, so let's determine if we're going to move a literal. Should we move a literal if r dot next boolean is equal to true? And keep in mind this is redundant, I just like being explicit. R dot next boolean and R dot next boolean equal true functionally are the same value. Because if this boils down to true, this is saying is true equal to true. It's doing a literal comparison. So this is redundant code by saying equal true. But it's not wrong. So if we should move a literal, then we're going to say the code at bucket I is equal to move, that's the actual assembly code for move, M-O-V. Then we need our source register. So we're going to say our source register is going to be, our destination register. So we're going to say our destination register is going to be some value between 0 and 3. So we'll say r dot next int 4. That'll give us a number between 0 and 3. Then let's concatenate on a colon. Then let's concatenate on, let's say the value we're moving in there is a value between, let's see, we're going to do 16-bit registers. So 0 and 65,535. If we're going to hold only positive numbers. That's fine. Fine for our example. So we'll say r dot next int 65,536 to get us a number between 65,535. So we'll put a little comment in here. This comment's going to say simulate moving a 16-bit unsigned int into a random register. Does that make sense? That's what this line does. We put the word move in there, M-O-V. Which register are we going to put this into? 0, 1, 2, or 3, randomly. And then what value are we putting in there? Some number between 0 and 65,535, because this number is non-inclusive. Else, here, I'll steal this line as our starting point. Should steal both these lines. We want to simulate moving a 16-bit, it should be into 16-bit register into a random register. And why don't we do this as a random register as well? So move a 16-bit random register into another random register. So we'll move r.nextInt4. We'll move into that guy, r.nextInt4. Now, we have an issue here, and that issue is, how do we distinguish when we're ultimately decoding this code on the CPU between a literal and a register? Well, if we're writing this as a language, just kind of a precursor for the, how many of you have had 470 programming language class? Oh, that class is a nightmare. You're going to love it. Okay, we actually write our own language in there. It's cool. So instead of using colons to separate here, I'm going to put commas to separate here, which is actually in line with what assembly language might look like. A line of assembly language might be move AX, comma 5, something like that. Okay? But we're going to be explicit here with our language. So we're going to say we're going to move into this register this value. But in this case, we're moving in a literal. So I'm going to say lit Actually, why don't we just do that guy as colon? It'll make it easier to parse. So lit colon the value. This guy down here will be reg colon the value. So now we've labeled, is this a literal? Is this a register? Make sense? Okay, so all this code right here is just giving us a randomization of what the heck each line of code in our program is going to be. Okay? And if we want to see the proof that this guy worked, right after we fill it, let's just go through and print all the lines out. All right, so we're going to remove this here in a second, but that code right there just is going to spin through the array and display it, and it should look like fairly random assembly code stuff. Okay. Let's go ahead and test this in driver. Here's our PCB. We say PCB or P1.display, but rather than display right now, we're just going to let the constructor show us all the lines of code. Oh, immediately. Username, password, 2 IO, 2 IO instructions. And then here's a bunch of assembly stuff. Man, look at all the IOs. Oh my God. I know, context switching like crazy. We probably don't want that many IOs. We want IOs to be substantially rarer than that. Not rare, but rarer than that. So rather than just flipping a coin here for should we do IO or not, why not say r.nextInt? Oh, you want to flip it twice? Yeah, that could actually work. If it's equal to true and r.nextInt, next Boolean rather, is equal to true. So we'll flip it twice. So it has to get 2 trues in a row in order for it to be IO. Okay. We'll call that a pretty decent mix. I'm okay with that. That'll let us feel the context switching. Okay. And then since this is a brand new process, the program counter will start off at 0. That's the first line of code we're going to be working with. And the process state moves to ready state. Okay. So we've dealt with the CPU registers. We're going to not implement scheduling information. We're just going to call that part of our algorithm that we're doing. Scheduling information is going to have some stuff in it about the priority of this particular process in terms of the scheduling algorithm. Initially, everything's going to just be first come, first serve for our simulation. Same thing with memory management information. Does this guy get a bigger footprint in memory? Blah, blah, blah. Counting information we'll never do. IO status information. Whether or not it's currently in IO is actually held by process state. Let's jump back to process state here real quick. So we're waiting. Now, is there a situation where we're waiting for something other than IO? Could be an event to occur as well. So for our intents and purposes, we're just going to call everything IO. Because really, even an event is IO. Waiting for an event to occur, for instance, a process might stop and say, I need to wait for another process to finish. So that kind of hooks into our inter-process communication world, where now we have, as a result of a fork, Abe, we have 2 processes that when one process is working on the CPU, if he gets to a part of the problem where he needs to wait for the result of another process, he might move into a waiting state until this guy signals him somehow that I'm done, you can go grab the piece of information from memory or something like that. We're just going to lump all that right now into an I/O event. Okay? So, for our intents and purposes, this is a PCB for our initial sample. Okay? And PCBs currently know how to display themselves with just the process state, but relatively, well, actually, let's go ahead and give it a little bit more. Let's say code length. This dot the code dot length. Program counter. This dot program counter. So we'll have process state, how many lines of code this guy has total, and then the program counter, where we currently are. Okay? And then we'll go ahead and run this and get our... So there's our process state. And if we want, we can create a couple more of these. And hopefully we see the randomness. So 4 different processes. So 4,708 lines of code, 1,427, 4,078, 1,426. Actually interesting that they are that close, but still different. Okay, so we have the ability to generate random processes now. Good enough. All right, so process control block looks like this. We just built it. CPU switch from process to process. So let's look at an example of how a CPU might work. So a process is currently executing. Okay, when it switches, we have an interrupt or a system call. Keep in mind, a type of interrupt could be you've run out of time on the CPU. Okay, and that actually might create something for us where you immediately go back to a ready state. So we might have to solve for that. So when we build into our PCB an interrupt, we might have to tell it where to go next. Do you go to a waiting state or do you go back to a ready state? But it gets interrupted. When it gets interrupted, we're going to save all the state from the CPU. So our CPU is going to have a copy. Well, I say a copy. The CPU is the original. So in our CPU, we're going to have, for our simple architecture CPU here, we have 4 registers. And we're just going to say that's the state of the CPU, remembering 4 pieces of information. Okay? So we're going to take those 4 pieces of information from the CPU and copy them into our PCB, our data structure, so that next time this PCB, this process, comes back to the CPU, we can load those registers back up with the last known values. All right? Then we're over here with our other process. This is process 0, process 1. So process 1 was sitting there idle while this guy was executing. This guy gets interrupted. We save the state. We reload process 1 state from their PCB. So there's 2 separate context switches going on here. Process 0 leaving the CPU, process 1 coming on to the CPU. Okay? Process 1 is now executing until it's interrupted. Save its state, move back to process 0, executing over and over and over again. So this is the back and forth between just 2 processes. So now you put 20 or 30 processes into the system. Now we have a CPU that, again, remember, one of the goals of an operating system is to keep the CPU busy 100% of the time. And one thing we want to get out of this slide is a certain percentage of the time, really a high percentage of the time, what the CPU is busy doing is context switching, moving from one process to another. So that's something we need to minimize. That's that kind of that variable, the balancing act we need to play. How long do we get to, how long does a process get to stay on the CPU before a context switch, such that all the processes feel like they're getting some CPU time, and we aren't spending all of our time context switching. Kind of see that balancing act there? So that becomes one of the primary jobs of an operating system writer. And we'll try to simulate that when we get our CPU written, where we'll have some variables that we can tune and change, where if something, for instance, let's say every process gets one CPU cycle in the worst case scenario. So it gets to get onto the CPU, gets to execute one instruction. You're done. Get out of here. So we instantly context switch. We're going to spend all of our time context switching because executing one instruction is not going to take any time, right? And we're going to try to quantify this through some sort of counter where we see that the amount of time we spent context switching was a much bigger number than the amount of time we spent actually executing. And that becomes problematic. Okay. So, this concept of process scheduling. How do we actually schedule the processes on the CPU? So, again, maximizing CPU use. Man, it's like amazing. I never looked at these slides. It's like I could see into the future. All right, so we're going to maximize CPU use. Quickly switch processes into the CPU for time sharing, so some amount of time on the CPU. So the process scheduler, his job, this is one of the primary components of an operating system. His job is to select among the available processes for next execution on the CPU. Now, we are going to initially write this so it's first come, first serve. Okay, you get in line. If you were first in line, you're going to get the CPU next. Where if we think about some more complex process scheduling routines, we might decide, okay, every process has a kind of an importance level. And based on their importance level, we're going to give certain processes, let them cut to the front of the line when they're in a ready state so that they can get CPU time ahead of less important processes, the steerage of the system. Okay? But for our initial one, it's just going to be first come, first serve. All right, so the process scheduler then maintains a scheduling queue. So we have the job queue, set of all processes in the system, all of them. Okay? So the process scheduler knows about every single process that exists in the system, whether they're ready, whether they're waiting, whatever. He knows about all of them. He has pointers to all of them so he can go and query them for various pieces of information if need be. We have the ready queue. Ready queue is the line ready to order at McDonald's. Line ready to get onto the CPU. Okay? Device queues, set of all processes waiting for I/O devices. So this would be the guys that are in a waiting state, waiting for I/O. Then we're going to have some sort of migration between those various queues. So when a job enters the ready queue, that's called a migration. When a job leaves the ready queue, goes onto the CPU, it's a migration. When he leaves the CPU, well, it's actually a context switch, but whatever. Okay? So we kind of understand the job of the process scheduler. This could very easily be a quiz. Hint, hint. And very easily I might ask you, what is the process scheduler and what is his job? What things does he keep track of? So this would be a pretty good slide to remember. And this is one of our core parts of an operating system, is the process scheduler. Okay, he's not just some nobody. He's in the starting lineup for our operating systems. All right, so here's an example of a process representation in Linux. So here's our structure. So we have something called a process ID, which we did not implement in ours. We probably should, we will, but we have to see how the process scheduler is going to store our processes first. Because process IDs need to be unique. Every process that is created has a unique ID that uniquely identifies it on the system. And as an example here, if I open up terminal and I go to top, we see here's a bunch of the programs that are currently running on the system. Each one has a unique process ID. Okay? Anyways, so it keeps track of the state. I'm not sure why the implement state is long. You're going to have to grow to a lot more states before it is going to grow out of a byte. But whatever. Time slice, this would be in a time division multiplexing for the CPU. That is, each process gets so much time. So in a process where we're going to have some sort of priority, where the queue for the CPU is actually a heap, we're going to assign every process a time slice. What percent of the default time do you get? Something like that. Oh, this process is parent, so you might be interested in this, Abe. So structure lists of children, so this would be like a linked list of all the children. List of open files. Something from the memory manager. And then the address space in memory associated with this particular program. Okay. What's up?
Wasn't that interesting?
I don't know. The process is parent, so it's kind of like if this guy, knows his parent, like in a biblical sense, and then we get down. That's Christian worldview, I think. All right. So in any case, this would be a Linux representation. I'm still confused on why this would be a long. It has to be for speed. There must be, if we assume a long is a 64-bit, it must store state in a 64-bit register or something like that. Because otherwise if we only need to keep track of 5 states, 0, 1, 2, 3, 4, we don't need a long to do that. Okay. So now, here's what the ready queue might look like. Now, before we actually dive into this, we want to kind of create our simulation. Because we're not going to be looking at an interesting version of the ready queue at first. We're going to be looking at a simplified version of the ready queue. So we're going to need a couple of other data structures here. So we're going to have the process scheduler. And we go back a few slides here. Process scheduler knows about all of the processes that are in the system, keeps track of the ready queue, and keeps track of the device queue. Okay, so really 3 different data structures. So we're going to have private linked list of, we're just going to store them as PCBs. Since really a PCB and a process are kind of synonyms for us. A process can't live in the operating system without a PCB. It's born as just a process, then it's immediately loaded into a PCB. So we're not going to emulate that step. So, or simulate that step. So linked list of PCB called the jobs. It's got to be a new linked list of PCBs. We need to import java.util. Okay, now for all of you who have not had CSC300 yet, when you get into 300, you cannot use this yet. You're going to be writing them from scratch at first. Then you can use this. All right, so linked list PCB, the jobs. We're also keeping track of the ready queue. The ready queue. Sounds like a barbecue joint. That's actually a pretty good name for a barbecue joint. I know. Seriously. I might be going tonight to Ashley's Q downtown. And then we have our device queue. That is dudes waiting for devices. All right, so I'll put a couple comments here. So next time we need to have each PCB register with the process scheduler. Some enter, well, all enter ready queue. Oh. Some enter device queue. All right, so come back and we'll continue on Wednesday. See y'all then.